In this section, our topic is 9.6, the ratio test and the root test. These tests are used for absolute convergence, although you can also think that you are using it just for positive series, which is basically the same thing. So theorem. Better. Theorem 9.17, called a ratio test. Let some an 1 to infinity be a series with non-zero terms. Such that actually it can have a few non-zero terms as long as after a certain point they are non-zeros, because that will affect the limit. Limit when n goes to 0, absolute value of a plus 1 an equals r exists. You take absolute value of the numbers, take a limit, and assume that we get a limit, and that limit is r. Then you have decision making. If r is less than 1, then sum of a n converge is absolute. If r is greater than 1, then sum of a n diverges. If r equals 1, inconclusive, it can go either way. What is the reason for this? I'm not going to write the proof. I wrote quite a precise proof in the note. Let me give you the flavor of what's happening here. Since we are taking absolute values, we can assume without laws of generality. Let's assume that an is greater than 0. As I said, otherwise I would carry absolute values. It's just cleaner this way. So what then? Assume that limit of an plus 1 over an when n goes to infinity equals r. And r is less than 1. Basically, this test is nothing else but a ready-made version of comparison with geometric series. Why? Because if r is less than 1, I can squeeze in some number, because if that ratio is approaching r, if that's your r, and those are these ratios, if they approach r, then after a while, they must be for sure less than 1. Because they can go up and down, but if you want to approach a limit, you are within some epsilon. So generally, I can squeeze in some number a between r and 1. So after a while, an plus 1 over an is always less than a, and that a is less than 1. And then what happens, then if your ratio is less than a, then we'll get the following, that basically an plus 1 is less than a times an. And then, so when that happens, so for n, let's say roughly, okay, put capital N, let's say that happens when n is greater than 100, then we'll get what? A101 is less than a times A100. A102 is less than a squared times A100, because we don't have an extra a, and then what happens? So a of n plus 100 will be less than a to the 100. And look at the n. A to the n times 800 So when we add them up, by comparison, this sum of an will be less than sum of 800 times a to the n. This is geometric series where the members are, where the ratio is positive and less than 1, so here is AR is equal to 0 less than 1. So this one converges, all converging by comparison. So that's basically the idea. I just, I was a little relaxed on that proof, but the idea is there. If you want to read more precise version, it is in the notes. But that's basically the idea, that after a while, when your ratio gets smaller than 1, you stay below a certain geometric series that's convergent, and you are still convergent. What if R is greater than 1? Then basically you can also do comparison with that series, but generally it's even easier to see that basically your series will fail divergence test. Because after n, let's say, greater than 100, as I said, 100 is just arbitrary to make it more specific to the capital N. If n is greater than 100, then we get an plus 1 over an will be greater than certain a, where a is now what? R greater than a greater than 1. But what does that mean? That means that an plus 1 is greater than an, actually. Because it's just greater than 1, actually. I don't even need a, it's just greater than 1, greater or equal 1. An plus 1 is greater or equal an. So that means your numbers don't go towards 0, they either stay the same or increase. So an does not approach 0. So you cannot have convergence. And then very often, unfortunately, it looks like, okay, if I am that unlucky to get R equals 1, then just this test cannot tell. It can go both ways. Unfortunately, most often this is what we get. That limit, even for harmonic series, we get 1. So even for harmonic, this test cannot help us. But in many cases, it can. And let me illustrate those. As I said, ratio test is really just a ready-made version of a comparison test. So here is a problem number 8. You get sum n goes 1 to infinity minus 1 to the n plus 1 times 4 over 2n factorial. This series obviously converges. It's so obvious from comparison test that I'm just a little bit hesitant to even run all these calculations. Why? Because look how fast denominator increases. So these numbers are really becoming small very fast. So if you compare it with 1 over n squared, you get immediately convergence. But doesn't matter. Let's play the game. So limit when n goes to infinity, absolute value of n plus 1 over an equals limit n goes to infinity. Usually when we do this, here's what we do. N plus 1, what does it mean? Wherever you see n, you put extra n. And make it sure that you do it carefully. So that would be negative 1. If I put n plus 1, n plus 1 would be n plus 2 times 4. Over here, you have to be careful. It's 2 times n. So here, if I put n plus 1, it has to be 2 times n plus 1, which is 2n plus 2. So it's 2n plus 2 factorial. And now I divide with an the way it was given. I'll immediately multiply by its reciprocal. So I'll take reciprocal here, minus 1 to the n plus 1. And then, of course, this just alternates the sign. Since it's absolute value, I can disregard those. So the only thing that matters are these factorials. And then we already saw this idea. Here's what we can do. Keep 4 here. 2n plus 2 is actually starts with 2n plus 2. Then you go 2n plus 1. And then those from 2n on are basically 2n factorial. So I'm doing this so that I don't need to open the second one. And then what happens, these two guys cancel each other out, and here it is. Now it's very easy to see that this limit is 0, because this is infinity for a huge number, for over infinity is 0, so we got the limit. And be careful, it's different than in the limit comparison test. In the limit comparison test, it will just get a finite limit, you're okay. Here, it's important if the limit is less than 1 or greater than 1. This is less than 1, so the series converges absolutely. All right, so that's how all this goes, and fairly trivial illustrations, nothing really big. Just let's see how all these calculations work. Here's something more interesting. So number 26. It's when n goes 1 to infinity and to the end. Actually, I don't know why I said it's more interesting. Because again, I will do it using the ratio test just to illustrate how it works, although it's quite obvious that this diverges by divergence test. Diverges. Why? Because, look, n to the n over n factorial is n times n. On the bottom we have n times n minus 1, 3, 2, 1. So obviously this is greater than or equal to 1. So what happens? Your individual members cannot approach 0. So forget about convergence. Doesn't matter, we'll pretend by the divergence test. Let's illustrate our ratio test. As I said, it's a little more work than necessary. It's a ratio test. How do you do it on the exam, however? As long as it's mathematically correct. So I'll take what? N plus 1 to the n plus 1 over n plus 1 factorial. So that's my number n plus 1. I don't need absolute value. And then take a reciprocal of the original one, n factorial here. And you'll see, this will be non-trivial calculation. So, I don't think the ratio test helps us. It more made us work hard. Look how much I need to work hard instead of using this elegant and quick method. I'll write n plus 1 to the n plus 1 like n plus 1 to the n times another n plus 1. That's power property. And n plus 1 factorial, that's standing trick again, n plus 1 times n factorial. So that first one is n plus 1, all the others are n factorial. Why is that good? Because when I have this, n factorial cancel each other out, that n plus 1 cancels n plus 1, and I have limit when n goes to infinity. What's nice is they have the same power, so I can get them under the same radical, the same power, n plus 1 over n to the n. And then maybe I can rewrite this as a 1 plus 1 over n to the n. And that tells you that basically what? This is a limit that we have in section 9.1. This is one of the most famous limits. This is E. And you know that E is approximately 2.71, which is greater than 1, so diverges. As I said, this is much more complicated than what we had, but again, I wanted you to see how the test helps you. By the way, the fact that we got that limit to be E has something to do with something called Stirling equality. If you Google that, you can see why is E showing up there. All right, and what about this one? From number 9, here is all this. Number 9, we will discuss sum of 4n, 5n minus 3 to the n, and it goes 1 to infinity. Again, I like always to estimate what's happening before I run into algebra and all that. Look, this basically, I'm not saying that this is correct, but just for my intuition, this behaves like 4/5. So this is basically like geometric series. So it's not easy to do comparison, not completely trivial, but I see it more like this. And that geometric series converges, so it looks like it converges, but let's do the ratio test. So we'll get the limit when n goes to infinity. What do I do here? Let me do this reciprocal. 5n minus 3 over 4n to the n. So my original number just flipped for a reciprocal. Here, be careful when you plug in n plus 1 for n. Obviously, n plus 1 will be here. And here I need 4 times n plus 1, 5, don't forget parentheses, minus 3. Here it is. So what would that be? It's a limit when n goes to infinity. What are we gonna do? It's gonna be a little tough here. My problem here is mostly that these two guys cannot easily communicate. But, so I would rather have the same exponent, then I can get them together and they interact. How do we resolve that? This extra one, I'll just put it on the side. So it will, or let me do the algebra first. 4n plus 4 over what? 5n plus 2 to the n plus 1 times 5n minus 3 4n to the n. That would be, as we said, that's the only chance I see to split one copy ahead. And then have n copies here. This guy will wait until we see what happens there. I can calculate that limit, but I don't know what will happen later on, so I would rather. So we'll get them together under the same end. And what happens is, let me be, I can factor out 4, n plus 1 times 5n minus 3 over 5n plus 2 times 4n. This is getting quite complicated. I must admit, look how bulky it is. So I'm not too happy with the way it works. But let's see. 4 and 4 cancel. So we'll get the following. Alright, this was our easy shot at it. I don't know if it's correct. Limit when n goes to infinity. 4n plus 4 over 5n plus 2. Now our FOIL here. So I get 5n squared times 5n. Plus 2n, and times negative 3 is negative 3n, and plus 5n is plus 2n, minus 3 over 5n squared plus 2n. Whew. Lots of work here. Limit when n goes to infinity, 4n plus 4 over 5n plus 2. This looks to me, this is slightly less than 1. So generally, I'd like to play this limit. 1 plus 1 over n to the n equals to e when n goes to infinity. Although it's not going to be n, so maybe more from calculus 1. Whatever x is a small number, 1 plus x to the 1 over x equals to e. That's the same thing. Because that x stands for 1 over n, then we get reciprocal. So I will here the 1 minus 3 over 5n squared plus 2n. We split it. And here comes the trick. If you want to use this, This is small, that's good. This approach is 0. You need its reciprocal on top. So I'm gonna build it artificially. I'll do minus 5n squared plus 2n over 3, so that I have reciprocal. That will be e, guaranteedly. Now let me balance things. So I need what? 3 over 5n squared plus 2n minus. So that's 1 actually. Minus is in front already there was. And then that n that I have. So now I start seeing that this limit will exist. So then I'll start splitting a limit. When n goes to infinity, 4n plus 4, 5n plus 2 times the limit. 1 minus 3 over 5n squared plus 2n times minus, yes, I have a minus here, minus 5n plus 2n over 3, and all that raised to the minus 3n over 5n squared plus 2. This is really important. So this guy went into power. This is my leftover here, I guess. So here with the easy division by n, I get 4/5. That's easy. This limit, according to the well-known fact, is just e. And then since exponential function is continuous, then this will approach e. What will this approach? E to the limit. Minus 3n over 5n squared plus 2. If I divide by n, it's very easy to see that that limit is 0. So it's 4/5 e to the 0. So it's 4/5. This is less than 1. So we conclude that it converges. Basically, it shows exactly what we saw immediately, that series behaves like 4/5 to the n, but the price we paid was heavy. And I didn't write that immediately. I think it's a good moment here to illustrate that actually for this series it would be much better if we use that second test, which is the root test. And I know that root test comes a little later, but here it really will show you how much better the root test will perform here. So you saw how complicated all this was with the ratio test. So let me formulate the root test and then apply it here, and you'll see how much better it will be. So the root test says the following. Theorem 918, the root test. It says the following. Let sum of an be a series and goes to infinity such that a limit of the nth root of absolute value of n when n goes to infinity equals r exists. So instead of taking ratios, we are taking nth root. Then what? Then, if r is less than 1, the series converges. The series converges. If r is greater than 1, the series diverges. It's the same decision making. If r equals 1, it's inconclusive. How would the proof go? The same way, take that limit, instead of multiplying, you are actually just raise them to the n and show again a comparison test with a geometric series. Again, this is just a different version of comparison test with geometric series. Then let me now use it from the problem number 9. Limit when n goes to infinity of and truth. They're all positive, so I don't need absolute value. And truth and n cancel each other out. 4n over 5n minus 3, n goes to infinity, and that's easy, divide by n, so we get limit, when n goes to infinity, 4 and 5, that's 4 minutes. That's less than 1 converges. Look how much better it was. By the way, just one comparison about efficiency. You know, the weakness of both tests is that sometimes they're inconclusive. So who is more general? Which test is stronger? They are basically this, we have similar strength. A root test is slightly more efficient, so there are examples, exotic examples, where ratio test is inconclusive and the root test gives you the answer. So root test is slightly more efficient. Which one do you use? I recommend both. If you see exponents, then use the root test. But if you see those factorials, then don't even think about the root test. Definitely do a ratio test. So generally each of them has its own situation where they dominate. Let me do a couple more problems and then we'll kind of comment which one is better. Or which one to use. Let's see, this was number 9, and we finish on this. So let's do number 66. Let's say we are just illustrating this. Number 66. Discuss the convergence of the series negative 1 to the n, 3 to the n times 2 to the n. Again, just looking at it, we see that it will diverge. Why? Because look, this is greater than 1. And this little n, yes, puts a little weight in denominator, but it's too weak comparing to exponential, so it will diverge. Let's run the test. I'll do ratio here. There's nothing bad here. So ratio test, we'll do the limit, and then it goes to infinity. Forget the minus 1 to the n because absolute value will absorb it. So we go to 3 to the n plus 1 over n plus 1 times 2 to the n plus 1. So that's n plus 1. Here we take a reciprocal of the n. And then we'll algebra carefully what happens. It's a limit, when n goes to infinity, there are n copies, and plus 1, cancel this, and here there's a 3 left. The same thing here, this is completely canceled, there's 2 left. So generally what we get at the end is 3n over 2n plus 2. Obviously this limit is 3 halves divided by n, so we get 3 halves greater than 1. Actually, it diverges absolutely, but I mean, it's not absolutely convergent, but it is not also even conditionally convergent, because once again, general member is not, individual members are not approaching 0. One more problem, as I said, now you just do the drilling to get used to the idea, and it's algebra. 1 sum 2 to the n over n minus 2 factorial n equals 0 to infinity. Again, I would, for this one, it's quite obvious that it converges because in numerator you just have 2's, on the bottom you have bigger and bigger numbers. So it's quite obvious that it will converge. Oh no, sorry, that was just something else. Sorry, I misread. This is an interesting technique. But we need some time. Let's look at this problem. So This is the series that starts at n equals 2. And sometimes it is convenient when n starts from 0. So just our software wants that or something like that. The question is, how do we do that adjustment or readjust the counter so that we get a series that starts at 0? And it's fairly simple. It's basically like substitution. So here, let me do it more in more details, and then I'll show you the shortcut. So generally, I will rename, so I will do new substitution. So n minus 2, I will call it m. So m equals n minus 2. So what will happen? Then from here, like when we do it for integrals, n plus 2 equals m. So here is the sum. So you will get 2 to the n plus 2. And then what's very nice, n minus 2 is just m, so we get completely clean factorial. But what else? Remember that idea I was insisting on it so much in chapter 8. When you do the change in the definite integral, adjust the limit. So the same thing here. So when n is 2, which is lower limit, n is 0, 2 minus 2, and of course infinity minus 2 is infinity. That means when b goes to infinity, b minus 2 also goes to infinity. So we go m equals 0 to infinity. And then of course, since this is what we call dumb variable, doesn't matter how you call it, m or n, so I can rename it back, it doesn't matter, and call it n goes from 0 to infinity, 2 to the n plus 2 over n factorial. And generally, I wanted to show you once what is really behind the scene, but what we very often do is the following. Let's see, here's all this. Here's what you do. When you want your index to go down by 2, then that's what you do. You push indexes 2 down, but then your variable goes 2 up. It's always in the opposite direction. So generally it goes 0 to infinity, and then this n becomes n plus 2 in the opposite direction, and becomes n plus 2 minus 2 becomes n. So that's like a quick, we call it shift of the variable, to do it on a run instead of do all this writing. But as I said, if you want to be on the safer side also, maybe you want to do the writing. All right. And then here's problem number 81. Again, one of those exotic problems that your book wants you to look. It says, determine the convergent divergence of the series defined recursively as a1 equals 1/3 and plus 1 is 1 plus 1 over n a.n. So what do you do here? Looks like we don't have, we don't have a specific formula, it's given recursively. So my question is, what can we conclude about convergence of this series? Generally, if I try a ratio test, that's okay, but here it is limit of an plus 1 over an, and then it goes to infinity. If you get an, it's just the limit of 1 plus 1 over n. And that's equal to 1. So if you try a ratio test, it's going to be inconclusive. But generally, there is no reason for anything fancy. So common sense always comes before any other machinery. So what is that telling me? So that's a nonsense, we're just wasting time. Look, we are all the time multiplying an by a number bigger than 1. So generally, an plus 1 is greater than an. So what is happening? Our sequence is increasing, so limit of an is for sure not 0, because functions that's increasing stays. So generally we'll have what? Our sequence will always be bigger than 1/3. You start with 1/3, multiply by numbers greater than 1, so individual drops are greater than 1/3, so of course forget the convergence, so there's no way that this will be convergent. So generally, with this technique, we are finishing analysis of the series of the convergence of the numeric series, we call them. So from section 8.7 on, 9.7 on, we'll study functional series, which is much more interesting and something really much deeper. But at this point, I know the dilemma for most of the students is, with so many tests that we learn, which one do you use? And I posted on Canvas one document where actually I give you the flow chart about making decisions and trying the tests. So I suggest that you look at it, and also let's look together at one list of the problems where we don't know which section it is. So this is from your textbook. So generally you look at the list of the numerical series, and you want to make decision, does it converge or not? So here is an interesting example 5 from your book. So number 8, sum of n plus 1 over 3n plus 1, n goes 1 to infinity. B, sum n equals 1 to infinity, pi over 6 to the n. Part C is sum n e to the minus n squared, and it goes 1 to infinity. Part D, sum of 1 over 3n plus 1 over to infinity. Part E is the sum, and it goes 1 to infinity, minus 1 to the n, 3 over 4n plus 1. And then part F is sum, and goes 1 to infinity, n factorial over 10 to the n. And part G is sum of n plus 1 over 2n plus 1 n. So here is the list of the series, and I don't know from which section they are, and I'd like to make a decision about the proper procedure to use and then to decide convergent or divergent. So for part A, what I see, and that's always the first, so yes, the first thing is actually that I always look at is, are the members positive or there is a sign change? The only one that there is a sign change is this one. So that one needs special attention. All the others are actually strength estimated. Because for positive, you just will it over. Because when you change a sign, it might alternate. For those with positive members, when you keep building, it just either overflows or stays up to a level. So I'm estimating strength. These members are too strong. Why? Look at this guy, individual. Its limit is 1/3, so it doesn't approach 0. So generally what? We'll say the following. Limit of an individual limit equals 1/3. It's not 0, diverges, nothing else. One of the main strategies you will see from that flow chart is recognizing geometric series. This is obviously geometric series. There is a fixed base and then running exponent, so this is actually geometric series. Geometric series. So the only question is the ratio greater than 1 or less than 1? Ratio is pi over 6, which is less than 1, positive. So converges. What about this guy? This guy looks like it could be, I would say that it's quite obvious that it will converge, because when you put this in denominator, it's such a heavy denominator that by comparison I can see that. I can also use integral test. I'm hesitant to use integral test because I'm always afraid that integral might be complicated. So don't rely too much on integral test. Do it That's one of the options, but I wouldn't rely too much on it. Although this one could be integrated because you see there is derivative ready, so you really. But the only thing you need to be careful is you need to demonstrate that the function is decreasing, and that's also quite obvious. So I'm not gonna do it, but just integral test. Although, as I said, comparison test. With which one? With sum of e to the minus n squared. This one obviously converges, and but it will be cleaner probably integral test. What about this one? So it will converge, this one obviously. This one will diverge. Why? Because it's easily, that's basically just variation of harmonic series. So compare with sum 1 over n, and you will get limit comparison. Their limit is 1/3, so it will diverge. Let me leave that one for the end because it has different flavor. What about this one? This one will diverge because numerator gets really big. So, so quite quickly these guys will be greater than 1. But it's probably quite inviting to do the ratio test. So if you do ratio, you will get, I'm rushing here a little bit, n plus 1 factorial over 10 to the n plus 1 times 10 to the n over n factorial. So this will be n plus 1 over 10. So when you take a limit, when n goes to infinity, n plus 1 over 10, you will get infinity greater than 1. So obviously diverges. As I said, it fails actually. Yes, we could have done it just divergence test. Take a limit of this, that limit is infinity, and that's it. For this one, it's quite obvious that we should do the root test. So limit, when n goes to infinity, when you take n root of this, you get n plus 1 over 20 plus 1, which is 1/2. So this is less than 1, the answer converges. So you see, these problems always actually send you strong messages. Wrong idea would be to kind of have your favorite methods that you insist on applying. Basically, problems always, different problems have different preferences. The last one actually that we skipped for a moment was this one. So what happens? Not absolutely convergent. Why not? Because if I take this absolute value, it behaves like this one. It would behave like harmonic. So compare with harmonic. Compare who? Not your original, but absolute value. 3 over 4n plus 1. But is it convergent? Conditionally, yes. Why? Because 3 over 4n plus 1 monotonically approaches 0, and it's positive, which together with this makes it alternating. So according to alternating series test, it converges, but conditionally. So after these 6 sections, it's very important that you kind of do that kind of development of the skill to find the proper method. And problems generally give us quite strong messages. So sometimes problem could be done with more than one method. In that case, just choose the one you like the most.